Welcome to the Consulting Specifying Engineer webcast, Critical Power, Power Generation Systems and High Performance Buildings, sponsored by ASCO Power Technologies. I'm your moderator, Jack Smith, with the Consulting Specifying Engineer, Pure Power, and CFE Media. In keeping with the American Institute of Architects' continuing education system policy, please take a few moments to read the quality assurance slide. Here is a list of the learning objectives for today's webcast. We will cover these in today's presentation. Now let's meet today's presenters, Randall Arrett and Corey Duggan. Randall Arrett is the Operations Director for ESD's High Performance Building Team. He oversees client relationships, project management, and quality control. He has provided electrical infrastructure design for projects such as the Prentice Women's Hospital and the Shirley Ryan Ability Lab in Chicago. Randy embraces technical design challenges and contributes to commissioning services such as new hospital blackout testing, and he is highly regarded as a speaker presenting at national conventions such as American Society for Healthcare Engineering for regional professional organizations such as Building Owners and Managers Association, and he is a board member of International Institute for Sustainable Laboratories. Corey Duggan is the energy modeling wizard at TLC Engineering for Architecture in Brentwood, Tennessee. He provides building performance simulation efforts across the more than 375-person firm for both direct project involvement and by supporting project teams on specific and unique modeling issues. Corey also provides modeling training for other TLC staff, and he is also a member of the Consulting Specifying Engineer Editorial Advisory Board. Thank you, Randy and Corey, for joining us today. And Randy, you're our first speakers, and the floor is all yours.
Thanks, Jack. So let's jump right in. There's lots of different ways that we can define a high-performance building. None of them are right, none of them are wrong, but for the purposes of today's presentation, we're going to define a high-performance building as buildings that are designed and constructed to facilitate operation and maintenance that both reduces carbon footprint and enhances the occupant experience. The end result should be a building that provides a healthy workplace environment that improves occupant performance. So high-performance buildings can come in all shapes and all sizes, hospitals, data centers, super tall buildings, even residences. And we'll do a couple of case studies towards the end of the presentation on Kingdom Tower in Saudi Arabia and the Shirley Ryan Ability Lab. But the bottom line is any high-performance building should drive life cycle cost and provide a good return on investment for the owner. They should always, interrelate the building's performance to unique function of the owner's goals. Most of all, they should create a healthy, safe, and efficient environment for the occupants. So no two projects are exactly alike, and therefore the codes that we apply to any two projects are never the same. It's important that you understand all the applicable codes and do a thorough analysis of national, state, local codes and ordinances to understand what you need to apply to your project. It is also important to review with the owner and design team what non-codified standards and guidelines are going to be implemented on the project. The bottom line is we need to drive compliance with all of our code actions. So our goals today will be taking a high-level look at a few of the commonly applicable codes. It's crucial that you fully understand the code's applicability to your project and how to properly apply them. So some of the codes we'll be looking at are NFPA 110, the standard for emergency and standby power systems, NFPA 101, Life Safety Code, NFPA 70, the National Electric Code, the energy codes, ASHRAE 90.1 and IECC, And we won't be digging into local ordinances and specialized standards, but it's very important that you look for the ones that are applicable when you start your project. So let's start with the energy codes. You know, in this day and age, I always look at the energy code as both our ally and at times as our antagonist. You know, I believe the energy code is aligned at the forefront of technology these days. Many of the mandates that exist around lighting densities and controls tend to dictate our design and remove some of the flexibility on our implementation. Some of the mandates, such as receptacle control that you see here for the ASHRAE code, can be very unpopular with our clients, and we need to take the time to educate our clients, make sure they understand why we are doing what we are doing and where they have options and where they do not have options. I think it's also very important that as an engineer, we challenge ourselves to strive for new levels of creativity. We need to look beyond the code and develop a holistic approach to systems integration. If we only do the code minimum, we are not a high-performance building. So let's take a quick look at NFPA 110, Standard for Emergency and Standby Power Systems. This standard contains the performance criteria for an emergency power supply system, and it defines a system as a complete functioning EPS system, including conductors, disconnect means, overcurrent protection devices, transfer switches, and all control supervisory and support devices needed for the system to operate as a safe and reliable source of electrical power. Additionally, there's three major criteria that define an EPSS in NFPA 110, and those are level, class, and type. The level 1 EPSS are installed where failure of the equipment to perform could result in loss of human life or serious injuries. So basically life safety loads. Level 2 systems are installed where failure to the EPSS to perform is less critical to human life and safety. So optional loads may be mechanical equipment, that type of thing. The class defines the minimum time the EPSS must be designed to operate at its rated load without being refueled or recharged. The type defines a maximum time in seconds that an EPSS will permit the load terminals of the transfer switch to be without acceptable electrical power. So how long does it take to transfer? This can be a little confusing when you try to relate it back to NFPA 70, which we'll get to in a minute. Things aren't always defined exactly the same way within these code sections, and you have to be very careful how you read them and understand how to interpolate between the codes. Some of the other relevant criteria following in NFPA 110 includes the testings of an EPSS. It requires an EPSS to be visually inspected every week, and it requires it to be run for 30 minutes monthly at 30% load, and it requires all transfer switches to be tested monthly. So there's a lot happening there that then gets applied back to other codes, such as NFPA 101, Life Safety Code. So looking at the Life Safety Code, it addresses those construction protection and occupancy features necessary to minimize danger to life from the effects of fire, including smoke, heat, and toxic gases during a fire event. This code also establishes the need for standby generators and emergency lighting for various occupancies. One example of that would be high-rise building occupancies. They're required to have standby power for electrical fire pumps, the emergency command center, elevators, certain mechanical equipment, especially that, that's managing smoke, and other equipment. As another example, NFPA 110, 7.2.3.12 requires Type 60 Class 2 Level 2 EPSS for new mechanical ventilation when required in the path of egress. And I'm sorry, that's NFPA 101. So going back to 110, that means 60 seconds or less to transfer, 2 hours of runtime, and that it's a less critical load. And so you have to kind of go back and forth between the codes to understand what they're requiring. As another example of the ways the codes are intertwined that are often confusing is NFPA 101 7.9, which dictates the requirements for emergency lighting. You need to dig deeper in the other codes to understand where it is applicable. Additionally, it requires emergency illumination to operate for a minimum of 1.5 hours. It is up to you to go back to 110 again and figure out what level, type, and class EPSS satisfies this requirement. So let's take a quick look at NFPA 70, the National Electric Code. This code is intended to establish minimum requirements for the installation of electrical conductors, equipment, and raceways. So we're going to take a little look at NFPA 70, Article 517, healthcare facilities, Article 700, emergency systems, and Article 701, legally required standby systems. So let's talk about Article 517, healthcare facilities. When you dig into 517, it continues our theme of complex and oft-confusing ways that codes are intertwined. This code must be closely reviewed in relationship to NFPA 99, which we're not even talking about today, which is the Healthcare Facilities Code. There's a lot of things within those that play off each other. And Article 517 also steps deeper into the way the EPSS are defined and discussed. Here they use the term alternate power source. So we talk about EPSS and all the other codes, but now we're looking at what's an alternate power source. And that's defined as one or more generator sets or battery systems, where permitted, intended to provide power during the interruption of normal electrical service or the public utility electrical service, intended to provide power during interruptions of service normally provided by the generating facilities on the premises. Now that's a real mouthful. How does that relate back to NFPA 110 level class criteria? Well, for that, you need to dig even deeper into Article 517. Now they start introducing the term essential electrical systems. Essential electrical systems for hospitals are comprised of 3 separate branches supplying a limited amount of lighting and power, and they're considered essential for life safety and effective hospital operation during the time of normal electrical service interruption. The 3 branches are life safety, critical, and equipment. So the life safety falls into one classification with NFPA 110, while the others fall into another. And so it's very important that you understand what types of equipment will be provided by each of these branches and how you interconnect those from a NFPA 110 standpoint and also an Article 700 and 701 standpoint. The other unique thing about Article 517 is it allows us some level of flexibility in how we configure the systems. We'll provide some examples of that later in the presentation. And also, unlike other areas of the code, Article 517 allows the engineer some latitude in sizing the EPSS, including the use of historical data and prudent demand factors. So we no longer have to size the unit purely based on connected load. So let's take a quick look at Article 700, which is emergency systems. This article established provisions for the electrical safety of the installation, operation, and maintenance of emergency systems intended to supply, distribute, and control electricity for illumination power or both to required facilities when the normal electrical power or system is interrupted, and specifically for illumination of essential for safety to life. Safety of life, human life. These are an NFPA 110 Level 1 systems and typically are classified Class 1.5, Type 10. So 90 minutes of runtime, start the load on emergency power in 10 seconds or less. The EPSS can serve optional loads as well as the code-required loads as long as certain criteria are met. And these criteria include selective load pickup, load shedding, and peak shaving. So basically, we have to ensure that the most critical loads, the life safety loads, are the default loads and are always on. It also allows for ground fault indication versus ground fault protection so that we don't have to trip out emergency power just because of the ground fault. Another mandate of Article 700 is that all emergency lighting be kept entirely independent from other systems, including raceways and barriers and switchboards. So a lot going on here, and you need to really dig deep into this code to understand how best to protect your system. Article 701 covers legally required standby systems. These are typically less critical loads than covered by Article 700. An example might be building pressurization or smoke management as required by 101 for high rises, as we discussed earlier, and also required for large places of assembly. The codes are fairly consistent with what qualifies for an emergency source. It could be storage batteries, generator sets, UPSs, separate services in specific occasions, connection ahead of a service disconnect, again, not always, but in certain occasions, and fuel cell systems. You might also look at local codes and ordinances because for healthcare, all of these don't always apply. Typically, most healthcare occupancies require diesel generators. And then quickly, Article 702, which covers optional standby systems. Some examples of this, what might be covered by this article, are HVAC systems or data systems that are not required for life safety. So let's look at an example. NFPA 101 7.9.2.2 dictates a Type 10 Class 1.5 Level 1 EPSS for use for life safety loads. NFPA 110 4.1 requires a Type 10 EPS to restore power in less than 10 seconds and carry Class 1.5 loads capable of running for 90 minutes. NFPA 700 outlines various sources for power that can be implemented as the EPS. So Corey, turn it over to you to talk about the approaches for HPB design.
Thanks, Randy. So now that Randy's gone through all the applicable codes, want to look at analyzing other types of generators or energy generation equipment that might be implemented in a high-performance building. But before we get into looking at any of those systems, the first step in any high-performance building design is to reduce the building load, because the size of these generators or other energy generation equipment is going to be driven by the amount of electrical load that the building has to make up with these systems, which is driven by the size of the HVAC equipment and other systems in the building. So the first thing that you want to do is try to reduce all of those loads, optimize the HVAC equipment, use energy models to optimize the envelope and its effect on the sizing of that HVAC equipment, along with the lighting systems and what you can pull together there. The optimization and reduction of those loads is going to lead to reduced first costs of both the HVAC equipment and any energy generation equipment. So this is something that really should be done before you even start to have the conversation about, well, what sorts of systems should we look at, maybe instead of just a typical standby generator, because really that can change where the conversation goes. So in keeping with that, you need to talk with the owner about, what is the project goal as far as energy generation equipment? Do you just want backup power meeting those minimum standards like Randy was talking about, maybe for a healthcare facility where it's going to be required for that specific building type? Or is it more that the building has net zero energy goals, or you have an owner that's really interested in looking at how that they can produce their own energy to reduce their energy cost, or maybe it's in an area that the electrical grid isn't reliable, so they would rather have something to produce energy on site that then maybe they could store or offset or provide back to the grid there. So it's important to have a conversation with the owner early in the design process to really give you the direction to figure out where these systems need to go, both from an HVAC standpoint and energy generation equipment. So going a little deeper into the implications of those goals. So a net zero energy building goal, that's going to drive you towards wanting to consider more electrically driven HVAC equipment, because even the most efficient combustion-based equipment, condensing boilers, condensing hot water heaters, things like that, those are still a little less than 100% efficient. So even a typical straight electric resistance heating system is going to have 100% efficiency because you're really looking there rather instead of cost potentially offsetting kWh for kWh or BTUs for BTUs. And so you really want to minimize what you're needing to offset in order to get to that net zero goal. So at that point, the energy source that you're using matters. If you're talking about reducing energy costs, then you may not care quite as much about, maybe that source or, whether it's electrical equipment versus gas-driven equipment or something like that. But you want to look at whether you can take advantage of something like the spark gap, and that really at that point you're shifting source to site. So rather than having, using BTUs or producing carbon at a facility that's far away and then transmitting that electricity, you would be reducing all those transmission losses, producing electricity on site, and inherently they're reducing your site EUI compared to what the source EUI was previously. So you need to make sure when you're doing that you're comparing apples to apples, that you're keeping your site energy and your source energy and you're comparing those appropriately. You also might want to look at utility incentives because different areas of the country, different utilities can really make one system more viable than the other. And you want to make sure that you're providing the best feedback and alternatives for your client. As far as net zero goes, if you're starting a project with a goal to get to net zero, you want to look at designing around an energy budget. So a lot of projects look at having photovoltaics for production of most of the energy in some of these net zero projects. So you may be limited by your roof area or area that you can mount solar panels. So if you know that that's the obvious one for your site or your climate, then you would want to figure out, okay, well, how much can we reasonably produce with the systems we can mount on the building or on the site, and then use that as a way to design the rest of your systems and know that you need to keep the energy consumption of the building and the other systems you design under that in order to achieve that net zero goal. Some areas it may be wind turbines versus photovoltaics, but it's really about seeing what's best for your climate, your site, most viable, and trying to design within that constraint. Now, you can use some combustion-based generation sources, combined heat and power, which we'll go into a little bit later in the slides. But in order for that to truly be net zero, you really have to be firing those with something that you've produced. You can't fire it with just straight natural gas or something like that and really consider your building to be net zero. So at that point, you would need something larger scale, an anaerobic digester producing biogas that then you could use to run through a combined heat and power system or even possibly a fuel cell to produce that electricity. Reducing the energy cost, continuing to look at that, the spark gap really it has to do with whether you've got low-cost gas and high-cost electricity and whether you can take advantage of that. I had a project that they had a really great gas rate to the point to where that basically they could put $30 worth of natural gas into a combined heat and power machine and get $100 worth of electricity out of it, just based on the way their rates were set up. And so you could look at that as, that you're essentially able to print money. And then the fact that if you have it in a combined heat and power situation or trigen situation, then you can also utilize the heat, which you're basically getting for free at that point. And utility incentives, you could use that and for places that will pay you more for renewable energy. So maybe you still want to reduce your energy costs, but you're going to use solar panels, and your electricity provider will pay you more for each kWh you produce than what they charge you, so that you'll get some savings due to net billing there. Renewable energy sources. The most common we see are photovoltaics and wind turbines that we can put on building sites, but those can be very specific per location and which one's more viable. Certain parts of the country just don't have sustained minimum wind speed to self-start or really make wind turbines viable. So the places that they are viable, they do a great job, and they often have grid parity with the electric rates. But in the rest of those areas, we typically look at photovoltaics. But there can be some places that you would assume, because it's a place you think is really sunny, that would be a great area for them, but it may not due to cloud cover. For instance, Florida, being the Sunshine State, has a lot of cloud cover that actually solar panels in Texas would produce more electricity per year. As far as the combustion-based generation type systems that you could put with either of those project goals, the two main ones that we look at are reciprocating engines and gas turbines or microturbines. And they both have sort of different reasons that you would want to apply them. These systems are best when used in a combined heat and power configuration, like I mentioned before, but you could potentially use them just as a straight standby generator. But really, the ability to utilize that heat load that's coming off of it, and specific building types such as hospitals, labs, and even hotels that have really high laundry loads, they can utilize that heat year-round. So you want to maximize the hours that you can use both the electricity and the heat that's being generated from the system. So typically we want to size those for the base heating load so that it can run at full load the whole time. Those two types of prime movers, which is the energy generation equipment, the reciprocating engine, pretty easy to maintain, something that most folks are pretty familiar with, but they tend to produce a lower heat, mostly hot water, not steam, and you want to look at the needs of the building and how much electricity you need to offset versus how much heat you can use. Reciprocating engines tend to be more one-to-one heat to electricity, whereas the micro turbines or gas turbines, they produce a higher level output, more steam, higher pressure there, which makes them a little more complex to maintain, but you do get more electricity out of them, so you might want to look at those in a situation where you have a lower heat load and need to offset more electricity. So I'm going to throw back to Randy for him to explain to you some different ways that you could implement these within system configurations.
Thanks, Corey. That's some great information you provided. Let's see if we can build on it a little bit as we look at different ways we can configure a distribution system for a high-performance building. Some of those might include automatic throwovers, double-ended switchboards, loop feed, emergency power systems, generators, cascading transfer switches. So let's kind of take a look and see what we can come up with. This is an example of a typical utility service with automatic throwover. So here we see two separate utility feeders coming into the site. An automatic throwover switch, so if either one of those services go down, power is restored automatically to the alternate source. And when it's restored, it will supply the entire bus of medium voltage feeders throughout the campus. Another approach might be to do two services coming in from the utility connected to a low voltage double-ended switchboard. Here what we have is a utility source feeding either half of the bus and all the loads associated with that particular bus. And then in an outage situation, you can automatically throw over to the other half of the bus so that all the loads are picked up from one side or the other. It's really important when you're looking at this type of configuration to understand how to size your buses. You need to make sure that that bus, when it's closed and we're carrying all the loads from one side, that there's enough capacity. If not, you're going to have to look at how you shed load when you go to a single source. And that could be done with a Kirk key interlock if you put a manual tie breaker instead of automatic tie breaker in between the two buses. Another approach that we use on some of our more complex and critical projects is a loop feed system. Here we've got multiple utility sources coming into the site, and they're feeding two halves of a distribution bus with a normally open switch in between, which would close automatically again on loss of utility power. But then we're also loop feeding those buses out to the loads and the unit substations that actually deliver power to the buildings. And what this allows for is if any feeder on site goes out, we're also able to pick back up load from the other side. So now we've got a level of redundancy and protection from a utility source failure, but we've also got a level of protection and redundancy from a failure within our facility. So let's look at a typical emergency power configuration. Here we see a utility source coming in to a switchboard and a generator feeding a switchboard. We have a single automatic transfer switch that transfers power from one source to the other to restore power. This could be a level 1 system compliant with NFPA 700 or 70700. Where all loads are served via a single transfer switch configuration, and all these loads would then be the life safety loads. We can start building upon this system by adding more transfer switches in, and now we'd have all of our life safety loads fed off of one transfer switch, and we could have optional loads fed off of another, where we could have, as in a healthcare environment, critical loads fed off of another one. And if some are good, does that make more better? Not always. What's also known as put all your eggs in one basket. This can cut both ways. If you look at a healthcare facility again, I can't tell you how many times I've gone to a hospital site and they tell me that they exceed code because 100% of their load is on the generators. So they picked everything up off their generators. Sounds good, right? Well, not so fast. The answer is it depends. A patient care area is required to be served by devices connected both normal and critical branch. To understand this requirement, you have to look at the single point failure on our distribution system. So we talked about making sure that no one feeder can allow any area within the building to lose power entirely. The same single point failure approach is applicable to many types of high performance occupancies. I always recommend a single point failure analysis be performed on every electrical distribution system. The results of the study really should be shared and discussed with the owner to determine where hardening of the systems might be desirable for their project. All of that's not to say that more transfer switches should not be added to the system. Additional transfer switches can be a very effective method to distribute the load to multiple smaller feeders and minimize the risk of a single transfer switch failure or causing a widespread outage. It can also be a very effective approach to add more load to the EPS with the capability of systematically shedding the least critical equipment in the event of an overload. So what else can we do with the emergency system? Here's an example of where we've got multiple generators tied to multiple buses, which are all then tied together with normally open breakers. And these could be automatic or these could be manual. In most cases, they'd be manual. Here, you could look at putting all your life safety loads on one of these buses, served off of a single generator so that they're all picked up in their block load. And then we can start looking at using maybe other types of alternate emergency power. Look at some of the loads, the types that Corey had talked about previously with fuel cells would be one example. And I see more and more where natural gas generators might be used. While those aren't qualified for healthcare, which requires diesel, the fuel generators could be one of your redundant generators and provide a nice alternate source so that, if you lose fuel, can't get fuel back into the site, you might always have natural gas. Another way of looking at the EPSS is to bring multiple generators in and parallel them together onto a common bus. This can provide a very high degree of reliability and flexibility in your EPS approach. It's a very effective method to utilize an N+1 design where one or two of the generators, in this example, two of the generators would serve the base load, and the other one would be completely redundant to the other two, so that if one of those generators go down, you can still carry 100% of your load. But keep in mind that Article 700 loads should be capable of being picked up by a single generator to meet the 10-second pickup requirement. Another option with this type of installation is use that +1 generator to pick up a little bit more of your site load on your generator system. And as long as you can shed that load in the case of a failure of a generator, still maintain your more critical life safety loads, you can add a lot of more power onto the system and give the owner a lot more flexibility. Another approach, again, providing a higher degree of reliability, is cascading transfer switches. So you may not do this for all the loads in the building, but maybe it's for the life safety. In healthcare, we often do it for the critical loads as well, where you've got two sources of normal power, and then you've got your standby generators, emergency generators. The utility sources would feed one transfer switch, which would then feed into the second transfer switch. So now we have to lose two sources of power before we have to go on to emergency power. Again, looking at level of redundancy and reliability, it all depends on your owner's requirements. Let's talk about a couple case studies. So what you're looking at here is a picture of Kingdom Tower, which is a project that's under construction right now. The two little black buildings on the left are something you may have heard of. It's currently called the Willis Tower, but previously the Sears Tower here in Chicago. And the Kingdom Tower is basically two Willis Towers put together. We call it a mega tall building. It's 1,000+ meters and 530,000 square meters. We have 9 MEP levels in this building. We've optimized it for performance based on these levels so that every section is independent of the others. And the way we've approached this is through a systematic configuration of looped power feeds. Let me dig in a little deeper here for you. Maybe you can see this. I hope this comes clearly across for everybody. But you can see we brought in multiple utility sources to the site. Each of the utility sources is tied together with a normally open, normally closed switch configuration. So that's all the blue wire. That then distributes throughout the building and hits unit substations that are double-ended so that one feed comes from different utility source than the other, and then multiple sources throughout the building. We do the same thing with the emergency power system. So we've set up two paralleling gear emergency power systems that then feed up through the building to unit substations, which are then interlocked together with manual ties so that we can always switch over to the other system if we need to in a critical situation. It was very, very important with a building this tall that we maintain power at all times to provide life safety. And so this was the configuration that we elected to use to help support that building. Another project that we finished up here recently is the Shirley Ryan Ability Lab. It's been crowned as the #1 rehab hospital in America by U.S. News and World Report every year since 1991. The 1.2 million square foot facility contains 242 private beds. One of the key owner criteria for this building was to provide the first ever translational research hospital where clinicians, scientists, innovators, and technologists work together in the same space. So what does all this mean? The owner basically dedicated a quarter or more of every floor to rehab therapy and research. And they created spaces like the one you see here in this picture. There are 2-story spaces where the patients are receiving treatment, but the scientists are actually sitting out on the same floor, conducting their research, looking for better ways to help these people, and in real time, taking it out and utilizing it on the patients to see what they can do. It's a really unique and beautiful facility. So based on the owner's criteria of, A, we've got a rehab hospital, and in a rehab hospital, the patients are there for a much more extended stay than what you would anticipate in a normal hospital. It basically becomes a second home to these patients. But they're not at the same level of acuity as you'd see in a lot of hospitals. They're not on life support. So this isn't an ICU type environment. Let's see. So what we had to do was look at ways we could support these patients in a way that they felt comfortable for long periods of time, had a lot of reliability to the power sources, but also could take on multiple different types of experiments by these researchers where they've used all kinds of power and voltages everywhere on that Ability Lab floor that we saw on the previous slide at any period of time, and they needed the ultimate flexibility. So the patients are overcoming life's obstacles to become a functioning part of society. Some of them have brain injuries, some of them have musculoskeletal issues, spinal cord issues, and pediatric issues. So what we did was we approached the electrical system where we've got 4 utility feeds coming in that are looped from the first floor all the way up to the top of the building in 4-hour rated shafts. They're all connected with an automatic throwover switch from the utility side so that we're restored within seconds of an outage. And then in addition to that, we've got multiple utility step-down transformers located in vaults on the primary MEP floors, both mid-level and at the top of the structure, that take that down to utilization voltages. The service switchboards in both locations create a robust infrastructure. We've got double-ended switchboards for all the life safety and critical loads. And we have medium voltage cables that are owned by the utility company, so the owner doesn't have to manage them. I'm going to run forward real quickly. We need to wrap some things up here. A couple other things that we really should consider anytime we're looking at a high-performance building is monitoring-based commissioning, where we leverage real-time energy data to keep the building running at its optimal state throughout the life of the building. And I'm going to move on through a couple slides and look at intelligent buildings, which I think is also very important if you want to classify your building as high performance. Here we're considering all the economic, environmental, and experiential functions within the building to create an environment where we embrace technology, intertwine all the systems together to create a building that enhances experience, both from an economic standpoint, so we're minimizing energy usage, environmental experience where we're maximizing people's interaction with the exterior and also using clean energy sources, and then also making sure that all the things that the users need to be successful are contained within the building.
Okay, now let's get to your questions. Randy, first question goes to you. Well, what is the difference between life safety, emergency, and legally required standby systems?
Thanks, Jack. So for that, we've got to turn back over to Articles 700, 701, and 702 of the National Electric Code. So Article 700 applies to the emergency systems, which are the life safety types of loads within your buildings. So those are required to be back on 10 seconds or less. Article 701 covers our legally required standby systems, which are from the less critical loads, as we discussed earlier. Things like smoke management systems or building pressurization systems, things that are important to have running in an outage event, but not necessarily directly related to life safety. And then Article 702, which covers optional standby systems, and those are the systems that you just elect as an owner or an engineer to put on emergency power, but are not required by code. Hope that helps, Jack.
Thank you, Randy. Corey, next question goes to you. what is the adoption rate in the broad commercial construction sector for high-performance buildings, and what is the breakdown geographically and regionally?
Thanks, Jack. So because, like Randy said at the beginning of the presentation, what one calls a high-performance building is can be a little bit different from person to person or from goal to goal. But I would say that I would look towards areas of the country that have adopted more stringent or more recent versions of the energy codes, whether that be the IECC or 90.1, because those areas are obviously able to implement those and stay more up to date. So they're looking at having to implement strategies that are above and beyond what the other areas of the country currently have in place.
Okay, Randy, your turn. Could you discuss how to integrate emergency lighting and life safety systems with backup power and building systems? Also, to discuss using UPS and generators as well as other backup power systems for smart buildings and building automation systems. No pressure here. No pressure.
Yeah, that's a mouthful, huh?
Yeah.
So that's an interesting question, and I'm going to refer back to one of our earlier slides to help answer that. Let's go back to this slide, which is a typical emergency power system with multiple branches. So when we're integrating emergency lighting and life safety systems, all of those are required to be picked up in 10 seconds or less. So typically on most buildings, we pick those up via a single transfer switch. And if we want to integrate UPS, which is always a great idea, then that would, I would typically put that on the load side of the transfer switch. It'll carry us through the outage, and then emergency power will be restored. Batteries will continue to charge, and we've got a fairly clean system to provide power. And that also then keeps that distinct and separate from the other branches, since we can't intermingle the life safety branch with other branches of the emergency power system. Another option that we see oftentimes is a UPS on one of the equipment branch, which is not required by code, but the owner often has data systems or other things that are required they require to be on because of the functionality of their space and their building. And again, you need to separate that out and provide that through its own transfer switch because it can't be intermingled with the life safety loads. Thanks, Jack.
Oh, thank you. Corey, we have time for one more question, and you get it. What do you mean by grid parity?
Grid parity. So that's a great question. Grid parity is what you refer to when the cost of renewable energy, or say energy generated by some source other than the grid, is cheaper than what you can buy from the grid. So that basically, if you could put solar panels or wind turbines in an area, and the utility rates are, possibly even incentives, or possibly that you could install them on your building, and that maybe the grid rates are so high that the overall cost for you to generate that electricity is lower. So, there's a couple different definitions depending on who you ask for what rates you use for that comparison. But the gist is that it costs less to produce energy with some renewable source than it does to buy it from the grid.
Good answer. I'd like to close by thanking our great speakers, Randy Arrett and Corey Duggan, for kindly sharing their time and their knowledge. I'd also like to extend a special thank you to our sponsors, ASCO Power Technologies, for supporting today's webcast. Finally, on behalf of Consulting Specifying Engineer, Pure Power, and CFE Media, thanks for attending the webcast.